Welcome to another unit in business mathematics. This time I'm talking about how we can calculate derivatives of functions with more than one variable. In the end, it's relatively easy if you already know how to derive a function with one variable, because what we simply do is we always consider only one variable as the currently relevant one. All the other variables are kept as constants. So if you can get the derivative of a function, which also has numbers or parameters in it, you can also get directly derivatives of functions with multiple variables. So for example, in many applications, there's not only one aspect, not only one variable, which can fluctuate, which can take different values, but for example, two or even more. So here in this example, we can have, for example, that the price fluctuates or the income of consumers, and this depends on how much you sell. Then we have a function of two variables, price and consumers, so P and M. Mathematically, we can have as many variables as we want, and we can relate them in any which fashion we fancy. For example, something like this here. This is also a function of two variables, and this looks as in a graph to the right. And you see here it's a little bit differently. It looks a little bit different than you already know this from variables with just one variable, function with one variable, because here we actually get three axes. Two axes, one for x and one for y, for our variables, and the third one, here the height, for the functional value. And that's why it's also problematic that if we have functions with more than two variables, to actually illustrate them. Because here we can still draw a three-dimensional picture, but drawing four-dimensional pictures already becomes a bit problematic. So we need to also find some way to actually not go purely with illustrations when we want to analyze functions like this. And for this, we first need to know how we can actually differentiate the derivatives for each of the different variables. Because if we have two variables, we also have two first derivatives. If we do this, we, as I said, cannot use the f mark xy anymore. Instead, we use one of these types of descriptions or notations. For example, fx means the first derivative of the function f with regards to the variable x. We could also write this as df by dx or del f by del x. The last one is particularly used if we talk about partial derivatives. That's a term which we use when we actually combine the different variables of a function, combine the different derivatives of a function for each of its variables into one, let's call this full derivative. So if we go with a total differential or something like this. So this works fine for one variable. What about if we actually want to combine first the derivative of one variable, then derivative of the other variable, or for example something like derive twice for x? Then either we could write the d's we have here, one more or twice more, so we could go df squared by dx dy, or we could simply, with our first type of notation, write f and then lowercase xy or xx. So for example, something like this. If we want to go twice for x, we just write f xx xy. And if we consider this for f and x and y, we would write it like f and then small xy. We can also do this for the example we already illustrated in the slide before. Here we have the derivative for x. So in this context, we kept every variable, in this case only the y, which is not relevant here, like a number, like a parameter. So this does not affect our result in any which way. Similarly, if we were to derive for y, then we would have kept the x like a parameter. It would look like this. And then we can continue and, for example, derive each of these functions again for x or for y. And well, that's then already everything there is regarding derivatives of functions with more than two variables. So it all boils down to basically keep the variable you're not, or the variables you're not deriving for, like constants, like numbers. Treat them like numbers and proceed as you know from the normal derivatives for functions with just one variable. So, well, this already concludes the session. So I say goodbye and see you next time.